Good afternoon. So we're moving on to the last topic that you are officially responsible for your midterm. That's basically hash. Oh no, I told you you're not, right? Sorry, you're not. Sorry. Yeah, no. So hashing is often done just before the midterm, and sometimes. So when you look back at the past papers, you'll see you're hashing on some of them and not on others. Right? It just depends on the timing of the midterm. So, sorry? It is not on this one. It is not on this one. I had actually declared that about 2 weeks ago, right? So anyway, but so what's hashing is actually a concept that spans multiple applications. In the context that we're talking about today, we're specifically talking about how you'd support a dictionary ADT. So if you recall, so far what we've talked about is you can use tree. I mean, you could use a linked list to support a dictionary, but it's no good. End performance. Instead, you could use a binary search tree. Binary search tree has a potential to do well, but no guarantees. So then we said, let's use a self-balancing binary search tree. So that was what red-black tree was. And then you have guaranteed order log-n performance for each of those operations, lookup, insert, and delete. So now what we want to do is look at yet another way that you could store a dictionary, data structure to back a dictionary. And this data structure sometimes is called a hash table, or in some contexts is sometimes referred to as a hash map. And the idea is relatively straightforward. We want to store key value pairs. Well, why not just set up a table to store those associations? So you want, can you actually read this? Is it dark enough? Yeah. All right, so let me persist to this color until it fades. So, remember that your dictionary is really an array or set of key value association. So in other words, something like that, where the K's are my keys and my V's are the values that they're associated with. And so far, we've just looked at this as, this could be a pair, for example, and then you put that pair inside of a bigger data structure in order to find the key. That's what we're talking about when we are discussing red-black trees. And there, the value that you're keying on is this set of keys. So this set of values didn't play a role. Again, in the hash table idea, those values don't really play a role either, but what we're going to do is take a more direct approach as to how this is going to be stored. So the idea is, try and use an array to back this. By an array, what I mean is a table that allows you order one-time access to any address you want. So, the idea is use an array to store key value pairs So that retrieval can be done auto one time. Now, of course, the challenge is if those keys are not numbers, or if the keys are not necessarily organized in any sequential order, then it's not so straightforward how to figure out where to put those key value pairs. In other words, what we really want, what would be ideal, is if we could do the following. We might store in our table values and somehow what we would get is a mapping between these keys and the addresses of the values. If we could do that. So this is the idea. The problem is that the set of values that the keys could take on, that's known as a key space. So that's a set of possible keys that you could have, is called a key space. The problem is that your key space is not necessarily always going to be numbers, and even if you could make them numbers, they may not necessarily always be legitimate addresses into this table. Moreover, so let's just capture what some of the issues are. Your key space may not be integers. You might be mapping strings, like a literal dictionary with meanings, for example. The key space may be very large. Relative to the actual number of associations being stored. And even if they are integers and they are small or few, it may not be that they map to the amount of space that you have. So they may still be bigger. So it could be relative to the number of associations you need to store, or also relative to the amount of space available. So for those reasons, we need to we want to try and capitalize on this idea. Yeah, can we get there in order one time? That would be fantastic if we could do that. But there's a small hitch. These keys don't look like normal addresses. So how to get around that is, and this is where the idea of hashing comes in, is we come up with a function that can convert our key space into an address space for the table. Okay? So the idea behind a hash table, or the solution to those issues, is to use a function which is called a hash function, to map the key space into the address space for our data. I had in mind the values, but you're going to see that we're going to have a problem. We're not going to get away with just storing the value alone. I'll come to that shortly. But the general idea is that we're trying to come up with a function to do this. So if I have to draw a picture for this, if this is my key space, and here's my table of values, then I'll have a function, which is my hash function, that produces addresses. So the idea is that for any key, for a key k, f of k is its address in the table. Now, let's talk about a few observations you can make with this idea, and that's going to lead to an important issue that we're going to need to resolve. And how we resolve it will determine what kind of hashing we're dealing with. So, at this point, based on what I've said so far, if your key space, all right, so first of all, let me take care of them one at a time. You could design a function to convert your strings or whatnot into integers. So that first problem, by designing a function properly, you can take care of that issue, no problem. The challenge, though, remains if I have many, many possible keys, and I now need to map to an address, I have a particular potential problem. What is that? If I have more keys than I have addresses, what am I guaranteed can happen? Assuming f is an actual function. So the domain of f is the entire key space. What's guaranteed to happen if I have fewer addresses than keys? I can't have keys without addresses, because then that wouldn't have been a total function. Functions, when a function defined on a domain, must have a value for every element in the domain. I will have more than one key mapping to the same address. Which principle is that again? Yeah, the pigeonhole principle that you learn from whenever. So there you go. You're wondering when you'd ever use that piece of math, right? Well, you just did. So pigeonhole principle tells us that we're guaranteed to have more than one key mapping to the same address. When that happens, we call that a collision. Now, of course, once you can have collisions, then that means that it's no longer safe just to store the value in the table, because if you have a collision, you won't know which of the keys that collided there was associated with that value. So what that means is that we don't get away with just storing the value only. In order to be sure, we're going to have to store the key along with the value. So, a couple consequences of this. By the way, I should have probably mentioned this. So let me just finish the sentence. If the size of the key space is greater than the size of the table, by the pigeonhole principle, you will be able to find keys, let's call them K1 and K2, that have the same address, hash value, we call that sometimes a hash address. So when this happens, this is called a collision. So this means the first implication is we need to store both the key and the value in the table. Let me call them KIVI. That's for all of them, not just the values. But we're also going to need to deal with the collisions. So I had interrupted myself when I started writing. There is actually a third kind of hashing, which we don't talk about much because it's quite straightforward, and that is if your key space happens to be small enough that it maps directly to the table, meaning that, okay, let's say you're running a little high school raffle, and you don't expect to sell more than 10,000 tickets. So when you number the tickets, you only use 4 digits to number those tickets. And when you sell them, maybe you take the phone number of the person you sold it to, so in case they win, you can call them. You might hash that. But with only 10,000, you could easily allocate a table of 10,000. And then in that case, you don't need to have collisions. If you do that, then that's called direct hashing. Okay? So, but that's a rare situation. It's not so usual that you will know for sure that your set of possible keys that come in to be stored in the dictionary won't exceed some relatively small number that you could just pre-allocate a table for that size and be done with it. The more common scenario is that you're going to want to allocate an amount of memory that kind of is proportional to the number of entrants that you expect. So imagine, remember, these are dynamic data structures. So as you're running, things are being inserted and then deleted. So if you're using an array to back that data structure, you have to remember that you're going to have to be prepared when that table gets full. You're going to need to allocate another array somewhere, copy over the elements, and set it back up into that bigger space. And maybe if you remove too many, perhaps you might want to reduce the space. That's not normal, but you might do. So there's a lot of management of these arrays going on behind the scenes. That's more common, okay? But I just want to mention as a by the way, there's another kind of mapping called direct hashing, where the table is small, you can store your values there. All right, so now we have two possibilities, well, in general, two categories of possibilities for how to deal with those collisions. In the first method, we're going to allow each cell or each address to contain more than one key value pair, if necessary. So in that context, you then view the array, the table, as actually being an array of, sometimes they're referred to as buckets. So think of it as an array of linked lists. A linked list is a typical way to implement that bucket, although theoretically you could use other data structures like trees or what have you to represent that bucket. Now everything that's going to be in that bucket is a set of all colliding keys, or the key values, the key value pairs for the keys that collide. So when you do that, that's called closed addressing or closed address hashing. Now, unfortunately, it's a very, very sad situation. And maybe now is not the time to tell you. Brought it up already, too late. There's this very confusing thing that they do where closed address hashing is also called open hashing. Whoops. And open address hashing is also called closed hashing. Yeah. So now what? Okay. So here's the deal. What I'll do in this class is that I will always refer to closed address hashing to mean what I just said, that each table is a list of buckets. The table is a collection of buckets. I'm going to draw a picture for that soon. I'm going to illustrate how that works and talk about the implications and all of that. But the reason I brought it up is that, I mean, as you should, when you finish a lecture, you might go online and look it up. Just want to make sure that when you look it up, you don't look at one thing and think you're reading for the other. Because the two names are, I don't know how that happened, maybe historical reasons, but they're both stuck. So they're both there. So you might go in literature and you want to read, and you say, what does this say again? It says something about close. All right, let me look up close hashing, yeah. And you get open address hashing. Or the vice versa. Okay? So closed address hashing. Closed address hashing. One way you can think of to remember it is that because it's called closed address, the idea of that is that what the address of the place you're going to store the key value is fixed, dependent only on the key itself. That will become a little bit clearer when we start discussing the alternatives. But let me finish with that discussion of closed address hashing first. There's a brief point that I probably should have emphasized right here. So, remember what I said before, that you're trying to use an array so that you can access the data in order one time. So you see here, if you're successful in implementing this function f very well, then if you can do this f in order one time, then notice that you would have gotten from key to address in order one time and then retrieve the data in order one time. So the beauty of it, or the allure of a hash table, is that you can get at that key value pair in order one time. Okay? That's the hope. What we're going to see is that that doesn't really quite work out unless you are partly lucky and also a little bit careful. So let's start now getting back to what we just started talking about, how to deal with these collisions. And as I said, you have two main categories. The first one is closed address hashing. And in closed address hashing, the table is an array of, let's call them buckets. Well, that is actually what they're called. A bucket is a collection of key value pairs, or key value associations. And importantly, well, the typically implemented as a linked list. So the picture then looks like this. So that's our table. This is our key space. I didn't necessarily mean for them to look like they're lined up. This is our hash function. Let me draw that a little bit. Let me make that look wobbly. And now what you have in each cell is really a reference to all the keys that collided. In case you can't read that, that's a linked list that has K1, V1 in it as first, K2, V2 in the second slot, and it might be more. So there's a, it continues. But the thing here is that these are all collisions. So in this picture here, F of K1 K1 is equal to F of K2 because you got a collision. So closed address hashing says, don't care how many things collide, put them in the same place at the same address. And that's why it's called closed address, because once you've figured out the address based on what F says, given a key, whatever F says the address is, that's where it has to live. Got that? So what would have happened is you'd have put in K1 into F, you'd gotten a number out, that number would have indicated where to store the key value pair. But because these entries are understood to be, in this case, linked lists, we would drop the key value pair actually directly into the table. Instead, well, linked list, so this is basically the pointer to the head of that linked list. We would have stored K1 and its associated value V1 into that list. And of course, the very first one, of course, is going to be a linked list with just one element in it. The next time, you just drop another element in, probably putting it before the ones that are already there. So, well, first of all, any questions on that? So how do I now look up an element? Question? How do I look up an element? Well, so to look up, well, okay, I just described insert. Let me write down insert. I just told you how to insert, but let's write it down. So to insert, into a table, the first thing is compute the address. By passing into a hash function. And then the next is to store the pair KV to the entry in the table at that address. Okay, so how expensive is that? How much time it takes to compute F, assuming F is fixed number of operations? If F is fixed number of operations and this key space is a finite set, then F is going to take constant time to compute, or it should. So this will be order one. How much time does it take to add an element to a linked list? Just sticking it at the front. Order one. So your total time looks like order one. And so now let's talk about how to look up. What do you think I need to do? Okay, so obviously I need to calculate the address. So I pass that to F. Calculate the address. And then what? Well, I'm going to go to that address and look. But what am I going to see? It's a linked list. Okay, now of course, that linked list could be empty immediately. What does that tell me? That key is not there. Yeah? Okay, if it's not empty, now I have a linked list. What do I need to do inside that linked list? Can I just grab the first element? Right, what do I need to do? I'm going to have to actually examine every element of that linked list. What am I looking for? I need to compare each element of the linked list with the key that I have. Because remember, all the ones that collided are sitting in the same linked list. Okay? So we're going to now need to search the cell stored at the address in our table for a key value pair with the key equal to the key we're looking for. How much time could that take? It could take order n. I hear people saying order n, that's very good. What would be required for it to take order n, n being the total number of elements that we have stored in our hash table? What would be the conditions under which that would actually happen? Every key would have had to collide at the same address, right? And then we store them all there. So, but this is theoretically possible. So, in worst case, this takes so we're n is equal to the number of keys stored. And of course, in the worst case, in this context, all the keys would have had to collide. Okay, so how about deleting? What do you think you need to do? To delete? You look it up, and then do what with that list? I have to search it, just like I did for lookup. And then if I do, then remove it. So I'm going to have to compute my address. Can I say equal to? Yes, I can. So I'm going to search for a key equal to k, and then remove it if found. How much time does that take? So order one to do the first computation. How much time could it take to do the search? Yeah, order n at worst. And then to actually do the deletion is just order one. So overall, order n time, worst case. Now remember, again, I'll just put a note here. Remember, in the worst case, for this kind of hashing, what we're saying is, for this to have been really order n, all keys collide. Let's talk a little bit about what instead of being so pessimistic about how bad it could be, let's talk about how good this could be. If I have a table of size M, maybe I should use H. You want me to drop off? That was my left. Suppose I have let's use H for my size of the hash table. Suppose H is the size of the hash table, and I have n keys stored in there. A couple things. What's the average number of entries that I would have in my list? I need some assumptions to be able to answer that question. What assumption would you like to make when I just ask that question? In order to answer it, what assumption do you need to make? What? You have to make an assumption about how the hash function maps keys to addresses. And so if we have the assumption that the total number, let's put it this way, the likelihood that a key maps to a given address is equal, then that's called a uniform hash function. So what we really want is uniformity in our hashing. And if we do have it, then now, in that case, what will be the average number of elements in that list, in each bucket? But if I have a table size of H and I have n elements stored, should be n over H, right? Okay, so let's talk about. So ideally, we want a hash function f that distributes keys uniformly across, or I should say over, addresses. Or another way, a practical way of looking at it, that is the total number of keys that map to one address is the same regardless of the address we're talking about. So in other words, it's as if this function f divides this key space uniformly across the size of the table. So now we're going to talk about why this works. Because right now, you might be saying to me, this is not better than a linked list, because the only thing that improved was the time to insert. We could do that in order 1 time. But look at this. Lookup is costing order n. That's horrible. You're going to do lookup a lot. And delete could cost me order n time. What is this? Some kind of sick joke, right? So clearly this can't be the end of the story. So what's going on? The point is that in the worst case, you really have to have all the keys collide. And now if you can come up with a function that at least guarantees this uniform distribution, then in fact you have a much, much better chance of avoiding this worst case. And so in other words, it's far more likely that you actually have, oops, it's okay. I'm still talking about closed addressing, by the way, but so suppose the size of a table is h, and let n be the number of keys stored. Then there's this ratio called the load factor. Which is sometimes you see alpha, well, certainly in some textbooks anyway, you'll see the symbol alpha to represent that load factor. Is the ratio n over h. Now the reason why that's going to be important here is going to be important for both methods. When we examine what the average length of the linked lists would be, the average length of the buckets. So note, the average size of a bucket is going to be the total number of key values stored divided by the total number of cells available. So the average size of a bucket is going to be n over h, which is your load factor. Now, if you can anticipate this, so if you know ahead of time, I know what my size is, I know how many keys to expect, then you can design your hash table to try to accommodate it. Now, why is this important? This then becomes the actual costs for your lookup and your delete on average. So on average, our time for insert, well, that doesn't change. That's still order 1. But the other 2 that depended on traversing or searching that bucket, that improves. So the time for lookup on average is now going to be dependent on the length of this linked list, the bucket. And if on average that bucket length is n over h or alpha, then the time for lookup looks proportional to that load factor. Likewise, the time for delete or remove, again, is also order alpha. Technically speaking, order 1 plus order alpha. The reason I put the 1 in there is because that alpha you could try and make that alpha get relatively small, go to close towards 0, but it's not as if your time actually goes towards 0 because you still had some other computations to do. So those will never go away. You have a constant time overhead, and then you have additional work to do that's proportional to the number of nodes that you've already stored. 1 plus alpha. That's what I was just explaining. Yeah, but I was just explaining it. Then you wouldn't have had to ask what it was. That's supposed to be also alpha. Let me write it again for you. Okay, so at the end of the day, the reason why hash tables are actually so commonly used is that this is typically the behavior you get. And so when you compare this to even your red-black tree, your red-black trees are giving you log n performance, excuse me, log n time performance for these. At least it's guaranteeing it though, it's in log n in the worst case. Hash tables, on the other hand, are telling you, in general, you're going to get nearly constant time performance, so much faster, but under these assumptions that you found a nice hash function and you don't have too many collisions. And how are you going to guarantee that? Well, sometimes you can't. You kind of have to know something about input or be very clever to deal with varying types of input in order to avoid this from happening. The good news is that in general, you actually do witness this. If you take an arbitrary data sample, put in a reasonable good hash function, you will observe this kind of behavior. And so in practice, hash tables are really, really efficient and really, really highly functional. Okay? So I'll see you in lecture. I'll see you next week. Remember, there's no lecture on Friday. Oh, and don't forget your midterm. We have midterm next week, Tuesday.